Hi, in this short video I want to cover the last two sections of Chapter 3 where it introduces two types of problems that are very common in linear programming optimization problems. One is the transportation problem, and that's typically when you have a series of plants, for example, that are producing products, and you've got a set of customers who are demanding those products, and each plant can potentially supply any customer. And so, however, uh, geographically they're dispersed, and so it depends on how far a customer is from a given plant, which will determine the ultimate transportation cost. And so you're trying to optimize that. That's one of them. And the other one is the assignment problem, which is a classic situation where you've got a set of tasks that must be assigned to a set of individuals or resources, and we we use optimization to make that assignment. So let me get back to the slides here. So the first one is the transportation problem, and it is the Big M company, and again they produce these products, these large turret lathes, and so they have each plant has capacity, and they've gotten orders from the various customers for certain amounts of each of these lathes. So the question is, how should we satisfy that demand? In other words, which plants should be shipping product to which customers? And so, let me go back. So the data that's given is for every origin-destination pair in terms of every factory to every customer. There is a given amount of distance, which drives then the cost to ship one lathe from one plant to one customer. So that's basically the 2x3 matrix that you see with the 700, 900, 800, 800, 900, 700 values. Now, on the far right is the output. That represents the capacity of how many lathes can be created by each of the respective factories. And at the bottom row represents the demand, the amount requested from each customer. Customer 1, 2, and 3, amounts of 10 lathes, 8 lathes, and 9 lathes. And one of the ways to kind of to illustrate it is to show the distribution network. You've got the factories on the left, F1 and F2, and you've got next to those the associated capacities for each plant. And then on the right, you've got the customers, and you've got the amounts demanded by each customer. And then along each arrow, which represents a network channel, basically, a from-to origin-destination pair with its associated cost. So now together, so we're going to try to, again, decide which factories should be supplying how many lathes to the various customers. So what we're going to do here is we're going to shell out to Excel, and I want to show you around the model that is developed for optimizing this. So the data is in light blue here. We've got the order sizes down here at the bottom. We've got the factory capacities here in light blue on the right. And we've got the from-to transportation cost per lathe that is shipped. So that's all the data that's been given. We've got the various named ranges on the right-hand side to make it easy within our formulas. So the decisions we're trying to make would be how many lathes should be shipped from each factory to each customer. So again, there's a total of 6 possible combinations of factory to customer shipments, and these values in yellow are truly what we're trying to solve for. So this sort of solution that I'm showing you right here suggests that factory 1 should supply all 10 of the lathes that are requested by customer 1. Furthermore, factory 2 should supply all 9 lathes to customer 3. And you'll notice customer 2 actually gets 2 lathes from factory 1 and 6 lathes from factory 2. In other words, it's not all just coming from one factory. But this solution represents the optimal the optimal assignment of these quantities to the respective plants. Now, the formulas in here are pretty straightforward. You've got total shipped out, which is just the sum for each row. You've got the amount being sent to a customer, which is equal to simply the sum of each column in that little 2x6 matrix. And your total cost is very simply a sum product of the decision variables, again, element for element multiplied times their per unit cost for shipping. And so that's nice and concise in that it's a sum product, the range shipping costs times the range units shipped. And so let's suppose we zero these out, and so we didn't have a solution yet. Well, then this is how we would run Solver. We would just simply bring up Solver. We would indicate total cost as the objective. We're going to change the range, which is called units shipped, which are the values in yellow. And there's two simple constraints for this. One is that the total shipped out must equal the output. So that's basically saying this column F must equal the column H, basically, element for element. And it's also saying we must satisfy all the customer demand, which is the total to the customer, which is the sum of each column times, must equal the amount demanded from each customer. We're going to use we're going to check the unconstrained variables non-negative. In other words, we can't make and ship a negative number of units, so we're going to check that box. And we're going to use the simplex method because it's a pure linear problem, meaning there's no variables multiplied times each other. And so then when we hit solve, it goes through, it indeed finds a solution. We're going to keep that solution, and it's the one that we originally showed you. Let's really quickly go through the assignment problem. So we'll go back to the slides here. For the assignment problem, again, it's a simple situation. We've got 4 temporary employees that need to be assigned to one of 4 possible jobs. And so the employees have different skill sets, they have different wage rates. So we're trying to figure out what's the minimum cost set of assignments that takes into consideration the amount of hours each individual takes to do each particular task, and also their associated wage rates. So again, they have given this in this case 4x4 matrix of the amount of time in terms of hours to do each of the respective jobs, and you can see it varies quite a bit. So for example, this graphics, for example, Joan takes 56 hours to do the graphics, but Ann takes only 41 hours. So that's quite, if it was only an hour or so different between each one, it probably wouldn't make a difference how they're assigned. But there's some pretty big differences within here. Also on this far right gives the wage rate for each employee. And so let's shell out to Excel here and show you how that looks. So we're now for the sell more problem. And so we've got, again, in light blue, we've got the data. This was the matrix that I just showed you, the 4x4, as well as the per hour wage rates. And these values, these ones down here, which are sort of demand and supply, they're kind of, if you think about it, kind of like that transportation problem we just did. And all that's just saying is the fact that this equals 1 means we have to assign somebody to do the word processing task. And we have to assign one person to do the graphics task and one person to do packets, etc. Furthermore, each employee can only be assigned and must be assigned exactly one task. This is what we call a pure assignment model in this fashion. So here's what we do. So we're going to represent our decision variables as this matrix of zeros or ones, where 0 if indeed that individual is not assigned that task, and 1 if indeed that individual is assigned that task. Now, a couple things. This is a feasible, it turns out, optimal solution that we're showing here in the yellow cells. But it turns out, Ian here is, you'll notice Ian is only assigned one job. In other words, only one value in that row is is set equal to 1, all others are equal to 0. In doing so, that satisfies the fact that Ian must be assigned exactly one job. Also, if you look at each column, there's only one selected in each column. That says because each job must be assigned to only one person. So again, it's kind of two ways of thinking about it. Each person can have only one job, and each job can be assigned to only one person. That's what the combination of these decision variables and their associated vectors of 1 on supply and demand. So with the now hours that we have at the top and our wage rates here on the right, we can create this intermediate calculation matrix, which is the cost. Basically, this $490 is the cost for Ann, who takes 35 hours and is paid $14 an hour to do that tasks. So you'll notice it's just simply D6, the 35, times I6, which is Ann's hourly wage. So these, again, these represent the cost of an assignment of an individual to a task. And now the optimization model is pretty straightforward. We've got a descriptive model right here. Our total cost is simply the sum product of whichever assignment you're going to make times the cost for each of those assignments. And that's what we're going to try to minimize. So if we invoke solver, we're going to zero these out. We'll just zero them. And now let's solve it using solver. We've set up the model, we've named our ranges, and so here's what we got. We're going to try to minimize total cost. So check the minimization button on that as well. We're going to change the variable cells, which are the yellow assignment named range. And the simple constraints are that total assigned must equal demand, and the total assignments must equal supply. That ensures us, again, one job, or the job is assigned to only one person, and each person is assigned to only one job. Again, we're going to check the make unconstrained variables non-negative, and we're going to use the simplex linear program for this particular problem. And when we hit solve, indeed, it solves it. We say OK, go back to our model, and there's our solution. So that's it in a nutshell. That's just two more linear programming formulations and showing you their solutions. But you should start getting the hang of it in terms of you're pursuing some objective subject to some constraints, and you're looking for a prescriptive solution to the set of decision variables that you've identified. So with that, we'll sign off and see you in the next class. Thanks.